all for showing up. My name is Magnus Parkos. I'm a professor at the Norwegian University of Science and Technology in Trondheim, Norway. And I'll present the work that I've been doing together with Audun Botterud, research scientist here at MIT Leeds, and Guillaume Tarel, now at IDF in France, previously at Hydro-Québec. So here we will dig into a bit of the more nitty-gritty details on some of the market structures within the electricity sector that hopefully will drive some of the investments needed that we have heard of in the two previous speeches. So our larger question is, maybe I speak too loud, is whether current electricity markets are sufficient to give investment signals in future low carbon power systems. And in this work, we use an analytical approach, simplified when it comes to the technical details, but we try to provide some insights. At least we try to learn a bit about how these markets work, also as a supplement to the large-scale energy modeling that we do, and many people as well use as decision support tools and analyst tools for large-scale decarbonization scenarios. So we have two previous papers that we've been working on. The first one, we added variable renewables and energy storage devices to an existing power system with thermal generators and derived the optimality conditions for this new system, and found out that short-term pricing will give optimal, the same result as the system optimum. While in the recent paper where we have withdrawn the thermal generators with firm marginal costs entirely from the system and only supply the load with variable renewables and energy storage, we find out that the prices are tied to the investment cost of the generators. So the existing energy-only market might not be, in theory, sufficient to give the incentives investment incentives needed. While in the case where we do have thermal generators, in theory, it works. So the question is, of course, does it work in practice? Well, our work here doesn't answer that. But if it does work in theory, at least we know that we have no clue about whether it will work in practice or not. So at least that's our motivation for this fun mathematical study. Okay, so in most power markets, they use marginal cost pricing for short-term operations, and of course it's supplemented by a lot of different additional markets. So traditionally, energy markets haven't, the price signals haven't been the only trigger to investment. We have capacity remuneration, we have subsidies for many type of generators, we have ancillary services that adds to the income, and so forth. And in some cases, we also have governmentally issued contracts for differences that drives investment. We, in this study, we look at the pure energy market solution, where the prices, the short-term prices alone should be sufficient to give the right investment signal for optimal solution. And this is, in theory, nothing new. I think that it's been This type of theory has been developed since the 40s in energy economy, showing that in for traditional system, the market solution gives the same result as the system optimum, where we have a central planners approach. But when we add variable renewables with zero marginal costs and weather driven and energy storage devices, which are operated on not a fuel cost basis, but storage value approach, we don't have necessarily the same conditions as were derived in the classical literature. So this is what we want to investigate, and we're also not alone to investigate those questions in a theoretical way. A lot of other interesting stuff to read in recent papers. So our power system is delightfully simple and very complex at the same time. So the traditional one, we just consider one peaker unit, one baseload unit to cover the demand, and we have load shedding to cover the loss, the extreme demand cases where it's not cost optimal to build power plants, at least for a cost minimizing point of view. And then we add VRE, wind or solar, and an energy storage. So the system optimal problem looks like this. We want to minimize the annual investment costs and the annual operation costs, subject to all realistic plant constraints, the system load balance, and storage constraints, and also weather availability for the VRE. And load shedding is then set to value of lost load or any administrative maximum price. So converted into equations, not going to go into details, but this is the mathematical formulation of this capacity expansion and operational problem. Keeping the system simple as this, it's possible to solve this without too much difficulties in an analytical way by setting up the Lagrangian and deriving the KKT conditions. So, which is a supplement to, of course, just implement it in a computer software and derive the result and look at the duals and try to figure out what's going on. Try to supplement that with some analytical work. We have some important constraints here. We have the load balance, where the dual of the load balance gives the power price, and we have an energy storage conversion constraint that makes sure that we are not using more stored energy than we charge. Simply speaking, we can set up the profit maximization problem, which is then to maximize the profit of each generator and unit here. And in the perfect market, we will get the same result as for the cost minimization problem of the central planner. So to very quickly just show that the classical solution to this problem with just thermal generators gives the optimal duration of load shedding and optimal duration of the peaker that gives the minimal total cost of the system, and can also verify that we get the same result when we maximize profit of the generator and check that costs are recovered. We get then 3 price segments: value of lost load or the maximum price, the peaker is the marginal generator for some hours, and the base plant for the rest. And then in our earlier work, we added cost competitive variable renewables to the system. Then we assume that in this case, wind power is so cheap that we will have some hours with zero price, meaning that we have to curtail some wind energy to keep the power balance. Then we have an additional price segment, which is 0. And at a certain point, we have the duration of the baseload plant, where we have to shut off the baseload plant, where when the price is 0, then the wind power plant is the marginal generator. And we can solve this problem with a new optimality condition for the wind power plant, which gives the optimal duration of the base plant in the system, and everything still works well in theory. And just short version, we add an energy storage device to this system, and everything works well also here. We have a short period of time where the energy storage is the marginal consumer in this case, bidding in the marginal value of stored energy, which is given by the efficiency and the cost of marginal generator where it dispatches. So cost recovery are verified and short-term prices are used. Okay, so what happens then if we remove, so this is my final part of the speech, what happens if we remove the thermal generator from the system and we only have variable renewables and storages and non-flexible demand? So then we will think that, okay, the prices will jump between value of lost load and 0, depending on whether we have enough renewable generation or not. But if we derive the optimality conditions for this case, where we take into account the storage constraints, the weather variations, and the capacity constraints of the storage, we derive at a solution where we find that we have two price segments where the energy storage is the marginal generator to supply the missing power between the load and the variable renewable output. And we have another segment where the storage is the marginal demand, charging up surplus wind energy, but not at its total capacity. And these price segments, the dual of the load balance, in this case, is a function of the investment costs of the wind generator and the storage. So there is so the prices are not decoupled to the investment. So short-term operation in the theoretical case has to be linked to the investment cost. The prices in the short-term market has to be linked to the investment cost. And this is not how the energy markets work today. So this is something that we have to reflect about. And if you set up, yes, wrapping up. So if you just put in this simple system in a computer model, minimizing the total cost, you will find these strange duals that can be hard to explain. But if you derive the mathematics here, you'll find these values that they are linked to the investment costs. So wrapping up is that we claim that still a simple low duration curve approach can provide some useful insight, which supplements, of course, more realistic studies. If we have thermal generators with no marginal costs, we can have in theory a solution that works well with short-term pricing. But if you just have variable renewables and storages, we are not able to find the optimal market solution without linking prices to investments. So our next work here now that we are doing is looking to how to connect this work with some theory of PPAs and long-term contracts to see if that can kind of be a part of the solution. Yeah, so with that, I'll wrap up. Thank you.
Just a question. So thanks a lot for your very interesting presentation. As you mentioned also here in the conclusion, you didn't take into account network congestion, basically the optimization of that. And when we speak about storage, you speak about the location of capacity, maybe the possibility to transfer power, no,
Yeah.
across the network can be an issue. So do you have an assessment or which do you think will be the impact of this assumption on a real market operated on a real mean? So do you have any ideas when you think about or we are planning to consider that congestion of the network?
Yeah, so I've done some studies on network congestions. So with using the analytical approach here, it comes with some limits, and then we step, I think, into we step into a territory where we have to use more complex models and to to be or we have to use the computer models to derive the results. But transmission congestions, that would be maybe for the storage owners. Okay, so prices, it depends on whether that leads to another, is it an investment signals? But if you just look at the market solution, if you add congestions, then the storage owner will just see the prices that are produced in their own price zone. So of course, if you have congestions, you will have, yeah, you can utilize more prices, but price differences. But the question is whether energy storage could be an alternative to grid reinforcements. And then I will then guess that you should get an additional payment for that from the system operator, from the grid owner. So you get an additional payment to add that service.
If I may brief a comment,
Yeah.
like the point you mentioned, so energy market,
Yeah.
if you have a storage company, you can decide if you want to offer one on the other or how you want to split your capacity.
Yeah.
So especially for the second network congestion for the grid structure.
Yeah, and we'll also add the ancillary services as well on top of that.
One more short question, yes. Yeah.
Thank you, Marcus, for this theoretical push forward that we need in the market. Could you elaborate a little bit more on the size of the storage that you have considered in the theoretical model?
Yeah, it's big.
Connected to the size of the volume of glass bottle.
Yeah. So in our there are some limitations here for the theoretical approach. We consider that we have a huge storage that we do have a energy constraint for the whole period, but we are not considering limitations on, for instance, 5-hour or 8-hour storage. Yeah, much larger, much larger. Yes.
How large does the storage become with theoretical model?
Yeah, that will be okay. So you have to verify that with simulation. Great question. I think that's typically a couple of weeks, maybe 3 weeks storage would be very close to what we have here. So this is long-term storage, hydro or hydrogen or yeah. Okay.
Thank you. Good time.